Okay, this will be a short video. My freebie software just gives me 15 minutes, so I just want to finish up on this large-scale structure of the universe. So we've built up to it here with our groups and clusters and superclusters. So we're going to zoom way out and look at the large-scale structure. When we put all of those superclusters together, this is kind of what it looks like, this web of galaxy clusters. So how do we know that this is what it looks like? We can't get outside of the universe. Well, what we do is we look at what we call redshift. And we've begun just sort of to introduce the idea of redshift when we talked about relativity and gravitational redshift, how gravity slows down time, and that makes light look redder. Well, it turns out redshift also has to do with motion. If galaxies are moving away from us, their light will look redder. We're going to spend some more time talking about that, but for today, just want you to know that it's a way to map the universe. We can look at the redshift. How red do these galaxies look? It tells us something about how they're moving and where they are. Look at the redshift of lots of galaxies, as many as we can see from where we are, to see where they are. How far away are they, essentially? It's a way to find distance, to see how they are distributed, the distribution across the universe of superclusters. So this first picture here on your screen is actual data. Each of these little pieces, the little red, green dots, are galaxy clusters and groups. The superclusters form these big filament things. Redshift here, these numbers tell us how far away the galaxies are. So we start here in the middle, this would be us, and then we look out at the sky and we get this picture. And it's a really interesting picture. So I'm going to scroll down here so you can see. This is a simulation of what this would look like up close, and this is an example. What we see is that these superclusters form extended filaments and walls. Okay, so the superclusters are not round, globular, like our globular clusters, but they are thin. They are filaments. Okay, so the superclusters come together to form extended filaments, and the filaments actually become walls surrounding voids. Alright, so walls around these voids. When I say void, I mean serious void. Right? Not just like the space between the stars, but space between galaxies, where there are literally nothing. No stars, no galaxies, nothing. That's what these black spaces are here. In the example, this is soap bubbles. So you wash your hands for 20 seconds, and you let that bubbles pile up in the bottom of the sink. And you get soap, films of soap, filaments that stick together to form these walls, and inside of that bubble, air, right? Nothing. So that's the picture here. It's a picture of soap bubbles, not individual bubbles, but all clumped together, right? So you have soap bubbles where the soap is the filament and the wall, and the void is what's in between. The superclusters are the filaments and the walls, and the void is what's in between. That's a lot of empty space out there, guys. Remember, we're thinking megaparsecs, huge, and huge empty spaces. So Another analogy is like a sponge, right? You have the spongy part, or the filaments and walls, and then in between you got the empty space. So think about those examples. I've got some videos that you can watch on what this structure looks like, and I'll probably put one in there too about our supercluster. And then you can answer our final clicker for this topic about going up in order of size, right? So we talked about groups, clusters, superclusters, and now these walls. So from smallest to biggest, put them in order, answer that question. That's it.